All right, here we go. So I want to talk about a topic that's probably pretty interesting for many who are working with robots that really interact with people, because you have to realize who is standing in front of you to really give people-centered services. And this work which I'm presenting here is available as a ready-to-use ROS package, the core people perception stack. And my colleagues, or my student Thomas and my colleague Jan contributed to that so that it's now available for you and so you can use it. Here, just an example why this is really important. So this just comes from a project we already had where we placed the care robot that you might have seen outside. We placed this robot in a care facility for elderly people. And apparently those old people forget to drink very often, and this is a tedious task for the personnel there. So we made this with a robot, that the robot observes the people, how much they drink. He has a logbook on that, and he's always serving drinks whenever the people don't drink enough. And so here's a short scene from this project. And because it's in German, you have to read what's below if you can't speak German. Just a second, probably. So the robot is now going to that table, and he's offering a drink to the lady. Let's see. Might be nice if it would start now. Okay, if not, I will just wrap it up. So the robot goes there, tells, hello, Miss Ebner, I have a drink for you. It would be really nice if you would drink now, because you didn't drink for the last 2 hours. And she's very happy to receive the drink from the robot, and we were all amazed that she really had fun and getting the drinks from the robot. So here you see, it's important from that point that you have a personal greeting, so whatever you tell a person has more force when you just address the people by their name. But also important is sometimes you might have a person in a wheelchair and not sitting in a normal chair, so you also have to adapt the approach pose, for example, how the robot goes along to the people and how the robot serves it. So some people might prefer if you go closer to them. And of course, if you think of all the elderly people, they also have to take medicine, so the robot could remind them for their certain medicine. So these are just some applications, but it's really important that you can recognize users when you work with these robots. So here's an outline what I will be talking about. So first, a short description how the approach works. Then I will talk about how the code is implemented and how you can interface to that code and how you can use it in your own scripts. And finally, I will show how you can also use it with a very simple interface. So, okay, so first thing is we are using RGBD cameras like the Kinect. So we have depth image as input data, and we also have color images as input data. And we basically do the following 3 steps. Like the first step is we go to the depth image and try to find heads in that image. And once we located the head, then we take this snippet from the color image. And in this image patch, we search for faces. And if we could find a face in that color image, we try to recognize the face. So we try to find out the name of the person who is that. So here a little bit more detail on that. So for the head detection, as well as for the face detection, we are using the Viola-Jones classifier. This is just a sliding window measuring in different scales on the window for heads on the one side and for faces on the other side. The Viola-Jones classifier is already available from OpenCV for faces. We already trained another one for heads and depth images, so this is readily available to use. So this component just manages to find faces and heads in the image. And the other approach is for identification, so we are using Fisher faces for this, basically, which is a projection-based method. That means just as an example, you see the big matrix of people. These are all people known to the algorithm. And now we do the following. We compute the average face by just summing up all faces. And then you can make a projection into a lower dimensional space, like using PCA or so. And then you get these so-called eigenfaces. And each of these faces shows some properties of some faces. And when you add them up, with the average image, you can reconstruct every of the training persons. What's interesting there is you have a weighted sum of these eigenfaces, and for every person this weighted sum is different, so this is how we really identify the people. And for Fisher faces, this is actually a little bit different. It is a little bit more intricate by better separating people that are different from images that come from the same person. So, and this is how we really realize to distinguish people. But these approaches have one drawback. It's that if you have different illumination, as you can see in the first image, or in the first row of images, especially in the last one, you cannot see barely any face. So we do some normalization on that by applying a gamma transform and then neglecting the first coefficients of the cosine transform. And then you see that the images look pretty nice. You can still recognize a face, and there it's much easier to really recognize a person. Another problem holds that the images need to be aligned for this algorithm, so the eyes always have to be at the same position in the image. So, but when you move your head to other directions, then we have to calculate this out, and this is by just detecting the eyes, as you can see in the middle image over there, and the nose, and then we virtually place the camera just in front of the head and get a better image, which improves the recognition quality. So let's hope that this video runs now. If not, okay, maybe the codec is not available, which is not so nice. Okay, let's see. Maybe this works in that player. Okay. All right, nice. Yeah, at least here it works. So you see the robot approaching to a table. We are sitting there in the lab, just talking a little bit, and now the robot recognizes our faces, which is pretty nice. And this is how training works. You just watch the camera, maybe move the face a little bit to show some different lightings, show some different positions of the head to the algorithm. It's like you need maybe 30 seconds or so for training. And these are the recognition results right then. You see facial expressions can be handled by this algorithm. You see here's a very bright lamp going around the face, and now you see it a little bit. Or here we also have a tracker in that, so whenever you move or when only your head is visible, your name still can be tracked, and even if you remove your glasses, it's still pretty reliable. So here's for a larger group of people, and there you see what the tracker does. So whenever a person goes out of the image, he tries to find it for a couple of seconds and then it just loses the people. All right, let's go back to the presentation then. Okay, and this is how it's really implemented. So what functions do we need? We need that we recognize persons either continuously, or some applications just need that you recognize them for a short time. So we can do both. We can capture training data for the identification, because you first have to tell the algorithms which are the people you want to recognize later. We have services for building the recognition model for either all people that are known or for just a subset of these people. And of course you can also update the labels for maybe you did something wrong, or you can also delete people from the database again. So, and we divided the whole algorithm into many singular modules just because this high modularity gives us the chance to replace single algorithms by then. So we can just pull out a node and exchange this with a better one if there is any. We also try to keep the interfaces pretty stable. So whenever you would like to replace one of the steps in the algorithm, you can just do this. It helped for us to make the teamwork even better, because we never had merge conflicts if one is working on the one node and the other on the other. One drawback is the message transfer overhead. You, of course, have to transfer more messages, but you can mitigate this by using nodelets. All right, and this is how it looks. So starting in the upper left corner, there's the sensor, which sends us a point cloud and an image. Then it just goes through a message gateway, which can just throttle down the rate of the sensor so that your computer has enough power for other stuff to do. And then we go to the head detector. The head detector finds those rectangles where it can find heads and copies the color images and transfers this to the face detector. The face detector detects the faces and copies the rectangles of faces into the same array. and forwards that to the face recognizer. The face recognizer now recognizes faces based on its recognition model, and then just sends an array of detected persons with label and position in the image and 3D position to the detection tracker. And this tracker just tracks people from one frame to the other, so that whenever a misclassification occurred for one time, this does not harm the real result. Yeah, and eventually all this data goes to the coordinator node. This coordinator node is just your interface to this pipeline. There you can just send a message like the get detection server that you want to get images once, or you can start the recognition, stop the recognition, set up the rate for the sensor message gateway, and so on. And what's also important is the face capture node. This actually captures the training images you need for your database. And I will later explain how this works. And the display is just for debugging, so that we can see what happens. Okay, for recognizing people, you can call the service start recognition if you want to continuously recognize people. In this message, you can just specify a target frame rate. So then all your sensor messages come or arrive with this frame rate, and if your computer is fast enough, your detections come with the same frame rate. And so you can decrease this frame rate just to give more power to other processes as well. And to stop it, you just send an empty message. And the other way would be you just want to get a couple of detections from the last 10 seconds or so. Then you can call the action get detections. And in this way, you can also provide a number of a timeout, for example. This means you want to search for 10 seconds, then you place there 10 seconds. And you can also place the latest age of detections, so that you really can be sure that you got the new message. And then the result that you get back is just a detection array of detections. Okay, and then the next one is very important, because when you start with a program, it's completely empty. So you need to train people to that. And it works very easily by either manual capturing or automatic capturing. So if you choose for the manual mode, you just call the action add data. And there you can specify the mode, and you have to provide the label of that person. And if you're in manual mode, then you call services for capturing one image each time you send the service. And if you want to quit, you just send a finish recording. And in the automatic mode, you just specify how many images you want to get and with which delay between the images. So it's pretty convenient to use. And the rest of the update labels and delete training data is also documented online, so I won't talk about this now. Finally, once you got all your training data, you just need to compute the recognition model. This works by sending this load model message, and this just takes a list of people names from you. And either you send an empty list, then it just uses all names that are available, or you specify, I just need to recognize those 3 people, then it just builds the model for those 3. So then I suppose that we have to start this further video like this. Again, okay. Okay, here's a demo, which my student just programmed. The idea is that the people here maybe can get a little bit louder. Probably not. Okay, or maybe here. Okay, so the CareRobot now is searching for a certain person. So it's moving to this group of people. Here you can see the sensor array in the head.
I'm looking for Yannick.
So and now he said that he's looking for Yannick. Now he's scanning the environment with his sensor that are mounted inside the head of the robot. Now we will see that he finds the first person.
Hey Caroline, have you seen Yannick?
Okay, it was not Yannick, it's not the right person, so he's searching further for Yannick.
I have found you, Yannick. Nice to see you.
Okay, and he's pretty happy that the robot addresses him with his name and is so polite to him. Okay, next one. Just for the usage, so it's pretty simple. You just go to this web page, download the software, compile. So I will make new releases very soon, but for the moment it's better you just take this one, because this is really, we added a lot of new stuff in that. So you go to this web page, download, compile, run a RosCore, start a Kinect driver, and then just launch the people detection. And then you have the possibility, we've written a manual client for just checking out the software, for testing it. So it's very simple to use. You just start a client, and then it just helps you in the menu. You can choose whatever you like to do, train new people, recognize people, change the frame rate, and so on. Or if you are convinced that it's the right thing for you, you can just use the messages and actions that I showed before and integrate this into your scripts. Okay, before I switch to my other machine that hopefully gets a connection to the projector right now, and I give you a short demo, just to wrap up, thanks to my colleagues, those two, we get this algorithm, and thanks for your interest in the topic, and while I'm answering the questions, I might prepare this demo and show it after the questions, okay?